Okie dokie, you're on.
So on today's agenda is Samaya Farid. She joined HAO this August. Before that, she was a postdoc at Yale University. Samaya graduated from Vanderbilt University in 2020, and she was a pre-doctoral fellow at Harvard CFA. Her recent research focus includes understanding the formation mechanism of solar coronal jets. And with that, Samaya, you have the stage.
Okay, thanks, Annie. So today I'm just going to talk briefly about some current work I've been working on to understand the initiation and acceleration of coronal jets. I'm going to give a little bit of background for those who are not really familiar with coronal jets, and discuss some of the currently understood initiation and acceleration mechanisms. And then I'm going to go into a deep dive of one of the jets that we observed in 2012, where we did both modeling and some observational analysis. So jets, what are jets? Coronal jets are comparatively small eruptions that occur in the solar corona. They are small compared to solar flares, which are a couple of orders of magnitude more energetic, but they occur very frequently. So around 60 jets a day occur in coronal holes, which possibly means maybe hundreds over the total coronal surface in a matter of hours and days. They are pretty energetic. They can reach velocities of thousands of kilometers per second, and they've been seen as far out as 3 solar radii. So we have been able to trace some jets from the solar surface all the way out to 3 solar radii using LASCO C3. So jets are small, but they are very, very mighty, and they could serve as a great laboratory for understanding magnetic reconnection in the solar corona. Also, the properties of jets are highly variable. It depends on where the jet is located. If it's located near an active region, like this jet here, this one is located on the periphery of an active region. So sometimes they have completely different dynamics and properties than those observed in the quiet sun, like these jets here, or in those in the coronal hole. In jets that are observed near active regions in X-rays are they tend to be hotter and stronger, because also that magnetic flux that is responsible for the jets tends to be higher, stronger near the base. So those jets are accordingly tend to be stronger than those found in the quiet sun. We've also observed jets in EUV, ultraviolet, violet, and white light data using a variety of mechanisms. There have been a lot of different studies on jets, some observationally based, especially during the X-ray, Hinode X-ray data era, and now with SDO AIA, we can observe jets 24/7 on the disk. But however, there does seem to be some difference between EUV jets and X-ray jets that appear only in X-rays. Some jets appear in both X-ray and EUV, but some jets only appear in EUV, and some jets only appear in X-ray. So that's one of the questions that are kind of outstanding. Through all of the statistical observational analysis that has been done, there are kind of 2 broad categories of jets that have come out of those. The first is what we commonly call a standard jet, and this category is basically is really based on the morphology of the jet that we observe in EUV or X-ray. The standout characteristics are this bright region at the base of the jet on the initial initiation, and that is called the jet bright point. Here we expect that reconnection is occurring on the outer region of this region as the jet emerges or is from magnetic cancellation into the region. This reconnection is happening here on the outside. Sometimes a filament is observed low down in the jet. That's not always the case, but often there is. And then the spire is often very narrow and very more pencil-like. Evaporative flows have been observed in these types of jets on the opposite edge of the reconnection, and that flow has been observed to be both observed as blue shifted and may contribute to other flow features, like some estimate that that flow might also contribute to the slow solar wind. So the primary difference in this region here, and then they're in the blowout jets, and blowout jets are a much broader spire, and here the reconnection is occurring in multiple places. So not only do you have reconnection here, lower down, internal reconnection, but you also have external reconnection as the jet forms in the spire between the overlying field and the newly emerged field. So in this case of blowout jets, they also have a cooler component often. And so this is a 304 image, and you can see the jet spire that is observed in EUV is also observed as a cooler component in 304. So this movie here shows a video of a blowout jet that was studied in 2016 by Panacea. And you can see the difference in this jet in the previous one that I showed. The main difference is that the appearance of the spire is quite different. And also the appearance of a filament here is more obvious in this jet. So often jets are associated with these filaments that you can see. You can see the small filament here running and making against this S-like shape. And this is possibly one of the distinguishing factors in these types of jets. Over statistical analysis that have been done and EUV, there seems to be a much larger population of these blowout jets than the standard jet. And that leads people to believe that possibly all of these jets are formed by filaments. And at some point, we would like to determine if jets do have the filament at all, if all jets have this filament at the base, or if it's just for some of the jets. So there are many unresolved questions that are surrounding jets that we are currently thinking about and working on. It's really important because I mentioned that the reconnection process and the energy partition is something that is throughout the corona. So it'll be good to understand what the underlying physical mechanisms are, whether or not these jets are formed from flux emergence or flux decay, how rotations impact the formation and evolution of those jets, and how the energy is deposited and accelerated after reconnection. Another big question right now is if all these jets contain many filaments, and if the jet phenomena can be traced to much smaller phenomena like spicules or mini jetlets, as what is called now. And really, it's still unresolved how much mass jets can contribute to the slow solar wind. And if these jets are the source of these Parker Solar Probe switchbacks, which are recently observed. So there have been several different approaches for understanding this. Some recent MHD models have been able to replicate some of the observable features, and 3 leading mechanisms have been identified to kind of categorize jets and help to understand their initiation mechanisms. The first is magnetic tension, and then the reconnection process that erupts after reconnection, the magnetic tension that is released. Then there's twisting or toroidal alphane waves, and then chromospheric evaporation. And so I'll go through each one of these in more detail next. So the first mechanism that people have kind of pinpointed to be responsible for jets is the magnetic tension or slingshot mechanism. And so what happens is that magnetic reconnection occurs at some point, either from flux emergence or flux decay. And as a result, the magnetic tension stored in these magnetic field lines push back, and that energy is used to accelerate plasma along the magnetic field lines. So the energy of the jet is primarily formed from the tension in the magnetic tension. And here studies have noticed that commonly found in jets are alphanic speeds in some very hot jets. And so we think that maybe in those cases, magnetic tension may be accelerating these jets. And another mechanism is the untwisting mechanism. So here, after reconnection occurs, one of the sources of energy that provide the acceleration for the plasma along the spire is the untwisting magnetic field. So what happens is that shear and twist and low down in the field, either through the formation of filament or sometimes just from a twisted field in itself. A non-potential field that has stored a lot of magnetic energy is released after reconnection, and then alpha waves can form along those reconnected lines. And because of the twist in the field, that tension along with magnetic pressure from the alpha waves contribute to the acceleration of the plasma through either shear waves or toroidal waves, either one, but a combination of those two mechanisms. A third mechanism is chromospheric evaporation. This mechanism is commonly observed in active regions. It occurs when reconnection happens high in the corona, and then accelerated particles travel down towards the chromosphere and interact with that cool and dense plasma. This causes an evaporative flow to move along back up towards the magnetic field lines, and that the presence of that flow there is driven by the pressure gradient between the magnetic field here and the different pressure at the base of the corona. And since that magnetic field is attached to both of those regions, then it experiences a pressure gradient, and so their flow is travels along those magnetic field lines. And so in those types of jets, we expect to see something like temperature increasing as a function of pressure, and velocity increasing as a function of temperature. And so even though this is commonly associated with active regions, it is possible that jets have enough energy to create this participation of high energetic particles that will be able to heat the chromosphere enough to create the upward flow. So there also have been models of this type of phenomena. Sorry, I'm just going to skip through that. Okay, let me go back. So let me summarize each of these three observational characteristics pointed out by the models. And for later on, I'm not going to talk about how we use these constraints from models to develop an observational guideline to determine what type of mechanism is at work for each particular jet. So again, in the slingshot only mechanism, where the acceleration is due only from the magnetic tension that is being released along the field lines, we don't expect to see a velocity dependence on temperature, and we expect the velocity of that plasma to be slightly less than the alpha velocity, a maximum of the alpha velocity. In the untwisting jet, we expect to see some evidence of twist in the field, either through a filament or through just a non-potential field. And then in that case, the velocity should reach close to the alpha speed. And finally, in the case of chromospheric evaporation, we expect to see a temperature-dependent velocity, and that velocity should be within the limit of the local 2.35, the local sound speed. This limit was derived by Fisher in 1986 for active region plasma, and we think that this limit will be indicative of chromospheric evaporation. So, or it could be a combination of all of these different mechanisms, and that's the complicated thing about jets. They could be any combination of them all, and so we try to understand how observations and a combination of observations and modeling can help us distinguish between these acceleration mechanisms. So that's what I'm going to focus on for the rest of the talk. So in the recent work that I'm going to talk about, we first look at several jets, and we look at the plasma properties and observational properties. We calculate velocity as a function of temperature to test for chromospheric evaporation, and we derive some common plasma properties like Doppler velocity, and none of them are broadening if we have spectroscopic observations. And then we also use a nonlinear force field model with the flux insertion method to construct a 3D topological coronal field. And here we can locate the regions of where magnetic reconnection is likely happening. So for the first part of this discussion, I'm talking about, we use a suite of different instruments that observe the corona from the UV to the X-ray. And we observe several of these jets through a range of temperatures. And from that, we can derive some understanding of the temperature of the plasma in the jet. So for this first part, we look at 6 jets that we observe first in the AIA and in a variety of locations. 2 of them are in active regions. Well, these other regions are in small active regions. So some people call them just large inferior regions, and then other regions are in quiet sun. As I mentioned earlier, jets features can vary a lot depending on the environment that they're born into, especially if the region is a strong magnetic field. So then the overlying field may impact the jet's eruption. So this is important to be able to distinguish between these acceleration mechanisms. So first we do a simple planar sky velocity calculation to determine the velocity along this spire. And we do that, take a slit along the jet spire and calculate the slope of that line, and that gives you the velocity. But we do this for each of the filters, the AIA channels, or each of the instruments that we use. So we derive velocity as a function of temperature. In addition to that, we take those observations and we calculate what's called differential emission measure, and which estimates the temperature as a function of the amount of plasma in the corona. So in this figure here, I'm showing how this is the temperature response function for AIA, and also 2 from XRT. So we take the emission in each of these AIA channels. We take the velocity in each one of these AIA channels, and then we also derive this modified 94 channel, which is primarily the iron 18 line in AIA, and that method was derived by Warren in 2010. And what it allows you to do is to extract the iron 18 emission using a combination of 171 and 193 and 94 channels, so that we can calculate the velocity of only the hottest plasma in the 94 channel. And you can see this is the temperature response function of the 94 channel, and it's double peaked. So it's a peak in the cooler regions around 6.1, and also is high temperature plasma. So if we take the velocity of this emission, we will get a convoluted answer. But in this case, we can separate the two, and we can calculate the velocities of the cool plasma and the velocity of the hottest plasma. The same thing is true for the temperature response function of AIA 335, and you can see the broad emission, the temperature response function here in the green line, but there isn't currently a way to distinguish between the iron 18 or the hotter, to isolate the hotter emission. So we derive this type of way to assign a temperature, one temperature for each of the channels. Like I said, the temperature response function of each of these bands is broad. It covers a wide range of temperatures. So we've derived a way of assigning a single temperature to each one of these band passes. So for instance, this shows the differential emission measure of along one slice of a jet, and you can see these 2 peaks. So if you just wanted to know the temperature of this jet, you can see these lines here show the range, or the error. You can think of as the error, and so you can see that it may be difficult to discern one particular temperature for this jet. But since we are calculating the velocity in each one of these channels, what we do is calculate the fraction of contribution to the intensity from each of those band passes. So we convolve this dm with the temperature response function and determine the fraction of contribution for each one of the band passes. So in that sense, for instance, and this is 171, we can see that these broad bands here indicate the amount of emission that is contributing. So for instance, you see that where the peaks are, that means that they are solid lines, and when there is no peaks, there are spotted dotted lines. Oh, I'm sorry. So in some cases, because of the temperature response function is very broad, or because the plasma is multi-thermal, we still cannot identify a temperature, or it's difficult to identify a temperature. But you can see in some cases, like for instance in 131, we can identify a temperature that is associated with that one band pass. So we use this as a way to define a temperature for each one of the band passes so that we can make the calculation of the velocity, to derive the velocity as a function of temperature, and to determine if chromospheric evaporation is there. Sorry, I skipped the wrong slides. So we also look at use iris to identify if there's presence of non-thermal broadening at the base of these jets, and that would indicate reconnection or some type of chaotic motion at the base of these jets. So if we have observations using iris, then we use those as well. We also check for evidence of rotation or filaments. If you remember, we said that one of the big questions around jets is presence of filaments. Filaments are present in all jets, and if they are the source of twists for all of the jets that we see. And for those jets that are very small, if it could be possible that their jets are, the filaments are also very, very tiny, and that's why we can't observe them. So we look for evidence of rotation in filaments in each of the jets by taking a cross section of each of the spires, and then looking for evidence of rotation. You can see oscillation patterns here that are pointing out in the white dotted lines here and here. And you also can look for evidence of filaments, and filaments would appear as these dark regions. And you can see this filament here that happened, they erupted below the jet, not within the jet, but below the jet, and the one above the jet, it shall appear here as well. In this case, you can see obvious evidence of rotation in this jet by these oscillating patterns. In this case, in this jet, we also see other interesting things, like, for instance, this jet went from emission to absorption, this plasma along here. So it's possible that this filament or this region of plasma is changing in temperature, or we're getting a different glimpse of the filament. So we did the same thing for each one of these jets that I showed in the first image, and I'll summarize each of the results at the end of all these, but these are the images for each. And so as a result of the observational analysis, we determined that here in the green is whether or not the jet had a filament. So only one of the jets did not have a filament. The rest of the jets had an obvious filament that we could observe. The jets that showed evidence of chromospheric evaporation was this jet that did not have the filament was the only one that showed clear evidence of chromospheric evaporation. And you can see that in this plot here. Here I've plotted the temperature as a function of velocity, and each one of these different color bars represents a different channel in AIA, and in this case also from AL poly and B thin from XRT. And so you can see as the velocity increases, the temperature also increases. Some of these channels are not, do not follow this trend. You can see this one here, which is 335 and 131. Like I said earlier, for 335, it's hard to determine a temperature because of the broad temperature response of AIA in 335. But for 131, we think that this temperature is particularly, this jet is somewhat cool in this pass band, or the most of the emission is not in this temperature range. So then we believe that this is kind of an erroneous temperature measurement right here. So, but the other channels give consistent results, and that led us to believe that chromospheric evaporation may be playing a large part in the acceleration of this jet. And coincidentally, it also, no, not coincidentally, but it also did not show any presence of a filament or twist. So the thought is that it doesn't have this additional energy being from the twist. However, it is being heated quickly, and these high energy particles are reaching the chromosphere and causing evaporation. And the magnetic reconnection, therefore, is not doesn't have to partition any of the energy to accelerate this large mass, or for the twist to take away any of the energy. Instead, all of the energy goes from magnetic reconnection goes directly into the chromosphere and causes chromospheric evaporation. For the rest of the jets, we found clear evidence that 3 are definitely not, are probably not accelerated from chromospheric evaporation, because there was not a strong temperature dependence. And in each of these cases, a filament was observed. So it's possible that the filament is either clouding the results of the acceleration, or that what is happening is that magnetic reconnection is occurring, and the energy from magnetic reconnection is being used up by the eruption of the larger mass, the twisted filament that is erupting. So a lot of the energy is being put into moving the mass around rather than heating. So that was the observational aspect of this. And so for these same jets, we also looked at magnetic model of these jets to determine if we could understand where the reconnection is happening. So I'm going to just discuss that a little bit. So since we know that the corona is tied to the photosphere magnetic field, we can use this to reconstruct a 3D shape of the corona using magnetograms. In this case, we use HMI, monocyte magnetograms, to generate a 3D model of the corona. So what a nonlinear force field model is so it assumes that plasma beta is low, which it is in the corona. So the plasma motions are dominated by the magnetic field. And so in that case, the current density runs parallel to the vector field B rather than across the field. So we know that the Lorentz force goes to 0, and this is called a force-free condition. And then we also know that the current density can be described by these equations here, where J equals some alpha B, and that alpha is called the proportionality factor. So it describes how much twist is along each field line. And so in the case of some models where alpha is 0, that means the field is potential. And these are commonly models used to create for global fields. Also, if it's constant, then that's a linear force field model. In this case, we use a nonlinear force field model, which we allow the alpha to vary as a function of position. And that will allow to have a more accurate depiction of evolving corona. So what happens first is that we take the line of sight magnetic field, in this case from HMI. Some people have used vector magnetic fields as well, but in this case, we use line of sight magnetic fields, and we insert a filament into the along the polarity inversion line. And here you can see the positive flux from HMI is shown in green and negative in red. And so we insert a filament along that polarity inversion line, and we compare that to the AIA observations and HMI observations to make sure that it's consistent with observations, to make sure that it's similar. And then what happens is that the model iterates the induction equation until this it relaxes, uses magnetofriction relaxation, and until it relaxes to a force-free state. And then we create what we can call a stable model. So that is one picture or snapshot of the corona in a stable 3D map. But then we increase the axial flux around the filament until we can create an eruption. And so what it does is simulate the motion of the filament or the field as is inputting non-potential energy into the field. And so we do that several times and tried several different ways to match until we match the observations. And so we did this for each of the, for most of the jets that I showed here. And just to show for comparison, this is the first jet that I showed you that we found evidence of chromospheric evaporation, but no evidence of a filament. And you can see that the model predicted by the nonlinear force-free field model is very similar to a schematic that we discussed earlier, where the reconnection is happening just at one location on the external region of the spire, and possibly formed lower down, but then moved upward. And then this is a very simple type of reconnection. As compared to other more complicated jets, where we have embedded these jets into complex fields. For instance, this jet was near a large filament prominence. And so it was, in this case, we had to model 3 filaments to try to simulate this eruption, and to try to understand the impact of the overlying field. And so in this case, we can see the jet is actually here in this image, and that box there is the same region blown up, and this jet here is the primary. This one here is the primary filament, and these other filaments were around nearby. And so we can use the nonlinear force-free field models to really get an understanding of how the overlying field impacts the eruption and how it generates what we see in AA observations. So we did the same thing for those jets. This is a sideways view of that jet that I just showed you in the previous image, and it really shows the complex morphology of the 3D field. We think that these regions here are magnetic null points where magnetic reconnection is most likely happening. So you can see that this field is this is the overlying field here, and then this is the jet that is emerging in this region, and you can see that the filament is buried down in here somewhere. And as the jet is evolving, for instance, in this image, these magnetic field lines reconnect here, and as well as interact with the overlying field, and to cause a very complex eruption. So in this case, we think this was sort of a kind of a 2-step eruption, where first we have this filament that is buried low in the corona, and as it rises, it causes reconnection here, and also those magnetic field lines interact with the overlying field here. So this is, now we'll discuss some of the analysis of this one particular jet that we investigated. And this jet was observed in 2012, and you can see that this jet is a blowout jet seeing the broad spire here. You can also see the presence of the filament, this dark region that is along the polarity inversion line. We look at, this is 193 in AIA, this is 304, and this is the HMI magnetic field. And you can see the positive and negative polarity regions that generate this jet. And first, I'll say that magnetic cancellation is contributing to the formation of this jet. But you can see in the first 2 steps where cancellation is occurring, we have some eruption, but the filament still remains, primary filament remains, but then magnetic cancellation stops. So that will be coming, and that will be important to note later. So as reconnection, the cancellation has stopped at this point, at the peak of the jet. So what happens is that the filament, we can see it begins to rise as cancellation is occurring, and as it becomes extended, we first see this faint eruption before the primary eruption, and it's maybe hard to see on the screen, but it's a very faint, broad eruption of cooler material. So we think that was a partial eruption of the filament, and then that precedes the main primary eruption of the jet, where we see the rest of the filament really escape and cause a lot of brightening and cause the spire. So in that case, we think that, as I said, that the primary, there's two different reconnection events going on here, where there's a primary initial eruption of low downfield, and then an outward eruption. So you can see that clearly in the magnetic model. So in this topological model of the same jet, it begins as we have inserted the filament here as the blue line down at the base of the jet. This represents the overlying field, and these magnetic field lines are only a selected amount of field lines that are in the model. We've selected here so it could be more clear. But so that you can see the overlying field is going in one direction, and then this is a closed field underneath this overlying field. And so as the jet erupts, as you can see here, you see this tangled mass of field lines that surround the filament. And so reconnection is happening at that location where the overlying field is reconnecting with the closed emerging field, as well as reconnection happening here, which is better seen in this image. And what we see here is a quadrupolar-like region where the filament has moved outward. And so now you have this reconnection point, which is identified, that the null here is probably that we can identify as a very strong reconnection point. So, and then the spire of the jet is formed. And I'm gonna show you this in a different way. So this is a movie of that eruption. And from here, you can see how the motion of the filament is affecting the formation of the jet. These still images is that movie, but in frames of that movie. And so I've outlined some of the regions that are most important. See, this is a closed field here in the yellow dotted line. The filament is shown in blue here. The overlying field is here. So the first null that we identify is between the overlying field and this closed region that is formed as the whole filament is erupting. The next null is identified here underneath the filament. And we know that it may have been, it's not to say that this null just formed. It was there possibly the whole time, reconnecting and forcing the filament to rise as an effect of that reconnection. Another null is shown here as the jet continues to evolve. This is also in between this newly reconnected magnetic field lines that were once tangled, but now they are more open, and so they are reconnected at this region. And this is a similar view of that region now. Well, because of the twisted motion of the filament, it's forced these magnetic field lines around in a circular motion. So you can really see the two different directions of the magnetic field, leading us to think that this is the same null point as shown here. If you look at it from the side, you can possibly see these regions a little better. So in the first case, where we see the magnetic reconnection between the closed field and the overlying field, we see that reconnection happening here, and you see that as the filament emerges. So in this eruption here, this reconnection point is what we think that first initial dark mass that we saw in the images, in the EUVE images. We think that is the first eruption there. So after the overlying field has been peeled away, lower filament, the rest of the filament in this lower downfield is able to move upward. And that also causes another point of reconnection between the overlying field, as well as a continued reconnection beneath the filament. The filament is lying along this channel here. And so you can see there's probably reconnection occurring here that is forcing that filament upward. And that force of that filament upward is interacting with the overlying field, causing all these several steps of eruptions. Finally, you see in the last phase of the eruption here, this figure that is similar to this quadrupolar region that we saw in the other image, where you have closed field again here, where it's reconnection, the field lines have reorganized. Now there's closed field here, and these are open magnetic field lines. So this would allow a lot of the plasma to be accelerated and escape along the open magnetic field lines. We also calculate something called the squashing factor, which is an estimate of how much twists are in these field lines. And this is a visualization of the previous image. The model, the nonlinear force field model, is fed into this simulation to show where the regions, which regions of magnetic field lines are most twisted. And so probably the most important thing to look at here is you can see that this twisted region here is prominent in observations as well as here. And you can also see these regions here that are dense regions of highly twisted field and high in current and enhanced current, regions of enhanced current. And so you can see as the jet evolves, that field evolves with it and moves upward as if similar to the eruption itself. So this is a still image of the previous one that I showed, because I wanted to show to these same, where these same null points region of null points are. So in the first nonlinear force field model that I showed you, I pointed out the null points, and this is the current sheet that we think is lying along those nulls. So this is the first current sheet that was responsible for the first reconnection event between the outer laying field and the emerging closed field from the jet. And you can see this current sheet evolve and dissipate. So here is not there anymore. It went from here and moved outward, and then this region, this is on the outer region, so it's not there. But then this other region appears. So this is in the secondary phase of the jet eruption, where this current sheet is from the lower region that had the outer region has now been peeled away, and now there's a lower closed region that is erupting. And so this current sheet we think is lying around within that region where that reconnection is happening. And each of these times you can see that the field lines are highly twisted in these same regions. So here it appears to be a kink in the field lines that evolves and moves outward. And that's similar to what we see in observations as well. So we also look at the emission measure of the same jet using AIA data, and we calculate the emission measure from the DEM, and to get an estimate of how the temperature of the plasma is changing as the eruption evolves. So on the left is showing the emission measure, how it's changing over the period of the eruption, and on the right is the evolution of the nonlinear force field model. So what's important to note here is that as you see this outer band here of hot or high dense or hot or both plasma that is associated with eruption is similar to what is often seen in active region flares, where you have field lines spreading, and that if we trace these magnetic field lines that are associated on the outer region, like here, so if we trace these original field lines, we can see that they are strongly related to this reconnection, this 4-quadrant reconnection region here. So that means that the heating that we see is very likely due to this reconnection region right here that we see in the 4-quadrant region. And that's causing all of this plasma to swell, and we can see the emission measure as a result of that heated plasma. So other authors have looked at the same event. Penasar looked at this event in 2017 and drew a schematic of what they thought was happening. We found a lot of similarities with their schematic, primarily that there is both external and internal reconnection between the outer layer field and in the inner field. The only primary difference is that the filament that they identified was only partially responsible for the eruption. So the primary eruption, instead of it being because of the entire filament lifting off, we think it's because first it was the initial overlying field that was peeled away, and then the filament could erupt, and that was the cause of the secondary eruption. So we did the same thing for several of these other jets, and we see interesting cases. In this case, there seems to be another 2-step process where the jet erupts very close to an active region. And as I mentioned, this jet was very strong and may be responsible for some observed high energy particles that were observed later in radio waves. But this jet occurred very close to the active region. And so we also think that reconnection occurred here, but also later in these regions where the jet further interacted with the overlying field. So it shows evidence of a complicated 2-step process rather than just one filament lifting off, as some of the jet models have depicted. So to summarize all of these different jets, the first jet that we looked at was a very simple model. The very simple jet, it showed no evidence of a filament, and it did show a velocity, a temperature-dependent velocity. So we think that the acceleration mechanism here is primarily chromospheric evaporation rather than a filament lifting off. And in the case of the second jet, we see evidence of the filament eruption, we see evidence of twisting, and we also see no evidence of a temperature-dependent velocity. So that would indicate that the acceleration mechanism is either the slingshot mechanism or untwisting, or a combination of those things to help accelerate that plasma. And the third jet, we also see evidence of of a filament, and there was no evidence of a temperature-dependent velocity. So it could be a combination of untwisting and evaporation here, because some of the channels did show some temperature-dependent velocities. I'll go back and show that if needed, but we think that because of this outer region is shown to expand, that is similar to active region flares, that may indicate evaporation as well. And so since some of those channels had some temperature bends, and we can see the evidence of these magnetic field lines expanding, then that may indicate chromospheric evaporation. So in this case, the last case, the fourth case, we saw evidence of a filament eruption, no dependence on temperature, no velocity dependent temperature, and so we think that tension and twist may be the primary accelerators of that plasma. So we did that for each of the jets, and for these jets, we also calculated the amount of free energy using the non-reinforcement field model. And what was relevant here is that we could see that the energy that was the total energy released here is increasing. So the free energy is increasing, which may explain why Jet 4 was also responsible for congruent eruptions later on. So in summary, we find that some of the jets show direct evidence of chromospheric evaporation through observations and through modeling to eliminate other possibilities. Some of the jets appear to be dominated by the twists or through the eruption of a filament. And so it's really not a direct, a simple picture of jets at all. So that was my last slide and have any questions.
Oh, thank you very much for the interesting talk. And just an FYI, I cannot see the in-person audience. I can only see the raised hands and questions from the online audience. So Samaya, please let me know, or please just address the raised hands from the in-person audience. Meanwhile, I'm going to ask all of the audience if there are any questions for the speaker.
I have a question.
Mm-hmm.
So thank you for the nice comment of this nice result. And I have a question about that simplest case.
Mm-hmm.
Did you insert a flux rope for that? So in the smallest case, which is very simple.
Yeah.
Did you need to insert a flux rope?
Oh, yes. So the question is, for this simple case, did we try to insert a flux rope? We inserted a flux rope for this one. So, so in this result that's shown here, we did not insert a flux rope, but we did try to insert a flux rope to see if. Yes, exactly. So we tried, but of course it didn't match the observations, so we eliminated that case.
But how did you form a current sheet? How did you generate a current sheet in this case? You just insert some potential field? You didn't insert.
It's just basically a potential field. It's basically, yeah, it's a potential field. So we tried a couple different things to see what matched best, and it's basically a potential field. Exactly.
Okay. So another follow-up question. Mm-hmm. So for those for the movie, you show the movie, the evolution, those are the ones that you couldn't get a full equilibrium. You just put in enough flux rope so they never reach an equilibrium, and you just follow its motion. As its number of iterations, you keep saying.
Yes, yes.
So you basically you let the force field. So you let the magnetofrictional model run.
Right.
Just through because it cannot reach an equilibrium, you just let it. Because it's non-equilibrium.
Yeah. So the question is, for the ones that they're showing eruptions, like this one, how do we construct this eruption? Yeah, the evolution.
Not putting the MHD model. You just solve the
right.
Continue to run this.
Right. Yes, it's not an MHD model. This is just allowing. So first we put in, yes, the filament flux rope, and then we increase the into toroidal flux until it begins to erupt. Exactly. Sorry. Oh yes, of course. This is next. Yes.
Are there more questions from the audience, online or offline? John?
Yeah, thank you very much, Maya. That was an interesting talk. I have a real quick question on the velocity. There were some different properties of the velocity based on the physical mechanism, and I wasn't sure I was seeing that in the plots, but I couldn't read the y-axis very well. So I'm wondering if the difference in the velocity was helpful to assess physical mechanism.
Yes.
And I'm also curious, what do you plan to do after this initial study? Where do you want to go next?
Yep. So this the velocity that we calculated here was first, it was a rough estimate because we did a line of sight velocity, and there are ways to do a more accurate depiction of velocity. So I'll try to do that first, and then we think that it seems like it's hard to determine what mechanisms are accelerating the jet just based on observations, just by looking at the jet, or just from looking at if there's a filament. So it needs a much larger study of jets in different environments to understand if chromospheric evaporation is happening, and this would be a quick way to do that. I developed an automatic technique that will automatically check for chromospheric evaporation on a much broader set of jets, 50 jets. So I'm calculating that now and to test the results.
Thank you. Are there more questions online or offline? Okay.
Sorry, is there a question raised here? Sarah has a question.
Yeah. So I had a question. You said earlier that jets have been observed out to 3, Arson and Lascaux. Do you have a sense of how high up how are they changing as they go up with height? And if you had a more sensitive observation, for example, when we get punch at the higher heights above the poles, would you expect, or wherever they are, would you expect to continue to see them? Is there a reason to think that they're expanding, that they're dissipating, or are they staying pretty colonnaded? And do you expect to see them? How high do you think you'll be able to observe jets?
Yeah, I think it depends on the jet. I think people have observed jets during solar eclipses that they extended as far out as the rest of the extended corona. And those cases, that jets stay collimated. But other work has shown, I think DeForest had some work where he showed that these jets can be accelerated along even further as they move away from the sun, like the solar wind. So I don't think it's not clear, but I think that some jets can be observed much further out, and which leads to the question of, could it be responsible for these switchbacks that Parker Solar Probe had been observing, and perhaps it's a possibility. I'm not sure.
Thank you. More questions? Online or offline?
Yes, one question here.
How do you distinguish between a coronal jet and jet from the solar eruption?
The question is, how do I distinguish between a coronal jet and a jet from like a different type of eruption?
No, like solar eruption and
Like a flare?
yeah.
Yes. Just from the question was, how do I distinguish between a solar jet and from other eruptions like a flare? And simple answer is just from observations. The jets, we consider them jets if they're small, much smaller than a flare, but the physical mechanisms may be the same. And so there's a whole range of eruptions that occur from flare all the way down to jets, to spicules, to micro jetlets, and this type of thing that appear to have the same types of mechanisms. So it physically, the physics of them may be exactly the same, maybe, but so in that sense, they're we only are using this idea of their particular size just from observational.
Just from the scale.
Yes, exactly, just from the size. Which that's also something that people investigate, whether or not these eruptions that we see here and consider them as jets, are they really the same as what they consider spicules? But spicules just a smaller scale. And then flares would be just a larger scale.
Thank you very much. Well, we are running up the hour, and I want to thank the speaker again for the interesting talk, and thank you very much.
Thank you.
Thank you.